So good morning. So Erlang is usually known for, and rightfully so, for big deployment backend systems because of its scalability power and everything. But this talk is about moving Erlang back from the cloud to the edge, to small edge devices. So I'm Sébastien. I already got presented, so not much more to say for it. I work for PREBUILT, GmbH. We are an Erlang embedded company. So our main sector is automotive industry and industrial automation industry. We have products that range from cluster of firmware flashing to smart conveyor belt. And we are partner in the Lightcone European Research Group. I'll go a bit more on that at the end of the talk if there's more time. So the structure of the talk will be first an overview of the hardware, of the GRISP hardware, a concrete demo, a concrete use case that could be done with the hardware. I'll do a presentation of the software stack that's actually running on the board. And I'll finish by a small update, an update about what we were doing recently and what's the roadmap after that of the GRISP project. So, but first, in order to break the ice and shamelessly try to grab your attention, I will show you some things that can be done with the GRISP board, some fun projects. So this is a robot that it's actually composed of two DC motors, a GRISP board, an ultrasonic rangefinder, and a battery pack. This is a very simple robot. I don't know. I mean, I didn't add time. I wanted to put a webcam or something so you would see it, but I didn't have time to prepare it. So, yeah. I explained for the one that do not see it. This is pretty simple anyway. So I just bootstrap the robot. The robot is actually connected through Wi-Fi. Yeah. The robot is activated. Let's see if I can. No, I didn't get the webcam, so feel free to see to go see. So this is a very simple robot that is completely made in Erlang. It's defined by something like 2 pages of Erlang code, so don't expect world domination behavior or anything like that. And its whole meaning in his life is scanning around for an obstacle, and when you find it, follow it. So I'll try to see if. He lost me. So, I need back off, see if. So, as I said, this is a very simple example of something done in 2 pages of Erlang. And your imagination is the limit there. So, this was for the quick. So, this is what you can do with GRISP. What about the hardware that is actually running on this robot? This is a GRISP board. This is a 300 MHz ARM processor, a Cortex M7. It has 64 MB of RAM. This is plenty to run Erlang virtual machine. It has standard Wi-Fi and a lot of connectors for sensors and actuators. I'll do an overview on this different way of the board has to communicate with the outside world. First and foremost, Wi-Fi. This is standard Wi-Fi, 2.4 gigahertz, with some extra power saving functionalities. It has deep switches and RGB LEDs, mostly used for debugging and seeing what's going on inside inside the software. 2 GPIO ports. GPIO ports are just hardware pins that can be customized at runtime as input or output. 1 UART port for asynchronous serial communication. 2 SPI ports for high-speed synchronous serial communication. An I2C bus, and a one-wire bus. So this is all the way you can communicate with the outside world from the GRISP board. So the idea behind the design of the board is to make a very flexible prototyping board, something you can use to quickly iterate over your hardware and software design. So this is why it has so much, this large choice of I/O protocols. All these protocols are accessible directly in Erlang. You don't have to do any write any C to be able to talk to this to the hardware. One very good thing too is that all these connectors that you saw on the board are standard connector that called P-mode that you can use to extend with lots of different kind of off-the-shelf hardware. So these are P-modes. P-mode is a standard that was created by Diligent, and they used to use it to sell pre-made extension hardware that can be directly connected in embedded devices, and this way extend simply an embedded device. So I'll pass over three examples of P-modes to have an idea about what can be done. So this, for example, is the nav P-mode. This is something that you just plug on the SPI port of the GRISP board, and it gives you three-axis accelerometers, three-axis gyroscopes, three-axis magnetometers, barometers with height and temperatures. HB5, it's H-bridge for DC motors. In the robot I showed before, we are using 2 of these for control each wheel. And GPS, so this one, you plug it in the UART port, and you have standard 3-meter accuracy satellite positioning. So as you can see, with just this GPS and nav extension P-mode on your GRISP board, you have absolute and relative positioning for whatever smart drone project, secret project you would have. And this is really, there's a lot of P-modes available off the shelf. This is just the offering of Diligent. The standard have been adopted by all the other manufacturers. So as you can see, there's like going from touch screen to speakers to card readers to whatever you can imagine. So I finish this overview of the hardware, saying like the basic things. The board is powered as a micro USB, and it uses micro USB for power and for console. So you can just plug it on your laptop over micro USB. It's automatically powered by the computer, and you have access to the Erlang console from there. So this is really simple to start working with it. It has a JTAG debugging port. So for people that know a bit more about low-level programming on embedded devices, this is a port where you can plug a hardware debugger. You can really debug the CPU. The objective of GRISP is not having to write C, so you shouldn't really require to use it. But you know that if you end up having to need to do some like low-level C driver for the GRISP, you have access to this kind of debugging tools. And finally, it has a micro USB card. All the software everything is boot from the micro USB card. Sorry, micro SD card. Everything is boot is all the software, all the BIM file, the Erlang virtual machine, everything is on a micro SD card. when you do a release and you deploy, you can deploy directly to the microSD card and everything there. So now about a real demo. Like robots are fun and things, but what we could do that a bit more concrete, something that could really show more something useful that you could do as a project. So this is just a GRISP board with a battery pack. The idea is to use that for doing home automation. So this is what we will demo right now. So first, I will show you how I will try to put it in a place. Yeah, in a place there. This is connected wirelessly to the network. So you can. I'll start by showing in a simple way. I'll first try to mirror that. Yep. Is it large enough? Maybe a bit more. Yeah. So this is a normal Erlang virtual machine that's actually running on the board. You can check that by doing a remote shell to it. Oops. I did something wrong. No, this was. Yeah. So I'm currently have a remote shell to the GRISP board that's there. So this is the content of the card to prove a bit that this is actually really there. I'll switch on the LED on the. Did it change? Yeah. So this is there. So now the idea is to use it as a monitoring device. On the GRISP right now, there's actually a web server. Right now, there's a cowboy running directly on the hardware of the GRISP board. We will go through where. So this is a web page that's actually served by the GRISP board. So this is a temperature monitoring application. So what we will do is actually add sensors, and we will so sensors that you would normally have all over your home for monitoring temperature. Right now, we will just pass a cable in there so just take the cable, pass it over there. This is a one-wire bus. So even though it's called one wire, there's a lot more wire there, but because we're only using 3 of them, because we're using power and ground, that's it. So I plug the one-wire bus. And now I'll pass some.
Sorry, which port is that plugged into?
Yes, this is a one-wire bus here. This is a port shown before. So then just pass around temperature sensors.
Are the sensors waterproof?
I think so. But I mean, I would prefer you trying this afterwards. And
You can embed them in like a rubber coating for submerging.
So right now, the board is actually polling the bus for sensors. It's interesting to know that in a real use case, you probably don't want to do that. You would probably want to first do a setup where you detect all your sensors. All the sensors have a unique 64-bit address. And so normally in a real production application, you would just, oh. Yep, sorry. So in a real application, you will probably want to only set up and scan and poll your bus for detecting all your sensors, and then keep their address and just communicate to the sensors. Right now, as for the sake of the demo, we do a polling every 15 seconds. So, okay, so we actually have our home automation and home temperature monitoring system working on. As you can see, you probably figure out this is Celsius degrees. So let's actually change that the Erlang way by doing some hot code loading on the GRISP. So let's open the project. This is an actual project that code running on the board, and we'll be look for the sensor, the code of the sensor that actually do the conversion from the raw data receiving on the one wire to the temperature. So one wire, this is this one wire DS18B20. So this is the high-level driver of the temperature sensors. Here, is it big? Is it large enough? Maybe a bit more? So here is the function that actually requests the temperature from the one-wire device, the one-wire sensors. And this is where it does the conversion. So let's actually do it in. So if I remember correctly, just if I do it, this is 1.8 times plus 32. Is it correct? Yeah. This is how you convert. Yeah. Well, I hope it is. I kind of remember it is. So I'll save the code.
And I see you divide by 16. What's the scale initially?
Yeah, the value the sensor give you is 16th of degrees.
Oh, okay.
So now I will open a rebar shell, rebar 3, on the project where I just changed the code. I put it a S name so I can join the cluster, rebar. Now I'll ping the GRISP board. So I joined the cluster. I made my rebar shell in cluster. Oh, sorry, in cluster with the board. So we are now in a cluster there. And now you just use the rebar 3 tooling to recompile your project. So the project is compiled, and you can now do a network load of the file that changed, that will be updated on all the machine on the cluster. So it was one wire DS18B20. Okay, so I updated the code in all the cluster. And now we should start getting new updates in Fahrenheit. This is 15 updates. I mean, if I just refresh here. Not good. So much for demonstrating code outloading. I mean, I already started, is there? Oh, but this. Let's see if I just save I properly save the file. Here, the file is saved, it's correct, yeah. I'm on the cluster. I am about 3 to compile. And I'm loading the code that is one wire DS18B20, one wire DS18B20. Sorry for the contract. The code is loaded on the GRISP. Oh, okay. So that's it. It should have been a lot smoother. Yeah, this got a bit more rough than expected. But yeah, so that's it. This is the idea, at least. This should work, and it is supposed to work like this. So I'm not exactly sure what happened and why the refresh took so much time. Maybe there's a lot more sensors, and because we're doing the polling every 15 seconds, maybe it took more time than expected. So that's it. This is for the demo and how you can do sensor monitoring on the GRISP board. It's actually just monitoring and just displaying temperature, but as it's evident that you could really actually do something out of this measurement, like control some heating device or something like that. So this is pretty much it. Okay. So I mean, if you want to try and heat up and put like on the exhaust and see that the value actually changed. So going back to the presentation. So about the software, what is the software actually running on this device? First, and very importantly, this is actually a real virtual machine built from an OTP checkout with very minor build-related changes on our side. And it's actually run directly on the CPU. It's really Erlang bare metal. There's absolutely no operating system in the middle between Erlang and the CPU. And to be able to do that, we use RTEMs. So RTIME is a real-time operating system. So I know I just said that there weren't any operating system, but this is because RTIME is really an operating system as a library. It is linked together with the virtual machine as in a single binary and offer an operating system-like API to the rest of the code. And one of these API is POSIX. This is why it made it quite simple to port OTP, the Erlang virtual machine to RTIME. So this is an overview about the structure of the software that actually running on the board. On the hardware, you have one big binary that contain BIM, the BIM virtual machine, RTIME, some extra library like libbsd and such. It contains all the C part of OTP, all the drivers. It contains all the low-level drivers or the GRISP runtime that are C drivers. And on top of that, you have all the BIM file, exactly like in any other Erlang distribution. So the BIM is the binary is loaded, run directly on the CPU, and load BIM file as would any virtual machine. So as a result, the stack is quite performant because RTIME is really well optimized for embedded devices. It has very fine-grained locking and high-resolution timers, and so this allows for something quite performant. It supports SMP, even so the board do not actually have two cores. It's a single-core CPU, but in a future version, or if you even want to build your own hardware based on this design, you could have a multi-core CPU and it will just work. And as a side note, we're actually using the FREEBSD network stack. So this, you know that this is some mature networking stack going on in the hood, under the hood. So about this GRISP runtime, I should have taken, there's no water. I didn't, okay, no problem. I'll survive. About the GRISP runtime, the objective of the GRISP runtime is to offer this hardware abstraction. The objective is to not have to write a single line of C code and be able to do embedded programming without any C code. So in order to do that, the GRISP runtime is split in two parts, the low-level driver and the high-level drivers. The low-level driver are very simple C driver that knows how to speak with a different extension port, a different protocol I described earlier on, like the SPI, UART, the GPIOs and things like that, the I2C and the one wire for this. So this is the low-level drivers in C that do this communication. And on top of that, there's a layer of high-level drivers that are in Erlang that offer a high-level API, simpler to use, to use the different extensions. For example, the HB5 PMOD we use for motors are controlled by GPIO. You can just use the low-level GPIO driver to say, okay, set this pin to 1, and this makes the engine go forward and such. But using high-level Erlang driver, you just say, okay, I want to use the HB5 on this GPIO port, and then you have an IP like forward, backward, stop, a lot simpler. And same for LEDs and deep switch. I think so. There's a layer of very high-level APIs that make it simple to do all this stuff. So that's it for the software stack overview. I'll go now a bit about update on what we did recently on the GRISP project. So as of March 2018, one very important thing is that we're actually now shipping hardware. After some hardware issue last year, in the end of last year, we now are able to ship hardware. And if you're interested, just go to the website and have fun with Erlang on bare metal. We updated Erlang to 20.2, so we have no bleeding edge Erlang running on the GRISP with support for SMP. So even though there's only one core, this is actually the SMP version of Erlang running on the board. The reason for this is that before that, we were using the non-threaded version of the virtual machine that would work just fine, but it's being deprecated. So if we want to be able to keep pace with the new version of Erlang, we have had to add support for SMP. And right now, this is actually done, SMP version on the brief. And as I said before, so all the low-level drivers are now implemented on the GRISP runtime. So you can use all the different protocols that are available on the GRISP. You can use it without doing C code. We added OpenSSL to the toolchain. So now we are able to do actually encrypted Wi-Fi. This is quite nice. It's basic, but you need OpenSSL for that. And thanks to the support in the virtual machine of statically linked NIF, we were able to compile and to provide the crypto module now on the GRISP board. So you can do crypto. And all in all the exchange I talk about, we will release an official 1.1 version of the GRISP software in the following weeks. All what I talk about is already available on GitHub. It's just there's no official release about it, but we will do that in the following weeks. So the roadmap for the GRISP project now, we want to do more high-level driver. So as I say, we support a small subset of this pmod extension as high-level driver, and we want to add a lot more of them. So make it really simple to do advanced stuff with the GRISP. And we're open to anybody that really want to submit a high-level driver to the GRISP project. Feel free to submit one, and we'll be happy with that. We want to add support for interrupts, hardware interrupts. Right now you can actually do hardware interrupts, but this is something you still would have to write some C to support it. And we want to offer a simple way of handling hardware interrupt completely in Erlang. We want to do that by having the C driver sending messages, Erlang messages to the process when there are hardware interrupts. This would maybe not be appropriate for all types of interrupt, but this will make something simple to have, at least to start prototyping something. We want to offer a pre-built version of OTP for the GRISP board. Right now, if you want to start your project, you have to build the GRISP toolchain, then build the OTP release for the GRISP, and we want to just reduce that as just downloading the OTP pre-built version for the GRISP and deploy to the board, and it will just work right away. This is particularly important for the use case of teaching in a class or some tutorials, something like that. You just don't want to spend half an hour just building toolchain and things like that. So this is something we want to do. And ELIXIR tooling. First, I would say that ELIXIR works perfectly on the board because this is standard Erlang virtual machine. But it's still missing the tooling, the way that right now is a rebar plugin, rebar 3 plugin. You just say, okay, rebar GRISP build, it builds everything. Rebar GRISP deploy, and it deploy all your application on the GRISP board. And we want to offer the same amount of simple way of using it with ELIXIR project. So that's most of the presentation. That's most of it. Now it's like extra things for if there's a bit more time. I will pass quickly over it until we are at the end. So things we are currently working on, interesting stuff related to GRISP. We are working on adding a real hard real-time to the GRISP board. We want to be able to do in Erlang things as with very high requirements of real-timeness. So we are doing that by adding a new Erlang scheduler in the virtual machine that we will run with a very high priorities, with some scheduling policy similar to FIFO scheduling policy. So that would ensure that when receiving a message, it will be preempted right away and handle the message. So we could have a driver, low-level C driver, send messages to this process where you would pin your handler, you would pin your Erlang process on this real-time scheduler, and you would be able to handle hardware interruption with very, very strict deadlines. And so this is something we are currently working on to add to the GRISP board. So, so as I said a bit on the beginning of the presentation, we are industrial partners in the European research group LightCone. The objective of this research group is to create models of edge computing using log-free programming like CRDTs and such. So most of the research in this group is done in Erlang. So we are actually providing them with GRISP boards so they can model edge computing use cases using the device. As part of the research too, we are working on our industrial use case. We have some industrial use case about having a mesh network of 1,000 Erlang nodes using high-size routing protocol to be able to communicate and discover the topology of the network. So this is part of the research that is going on right now. And as part of this too, we are working on fixing the edge, fixing or reducing the impact of the head-of-line blocking. That is a lot more. That has a lot more impact when you have a mesh network of nodes. And well, I think that will be so. This was for the mandatory graphics, just showing that our current prototype of packet fragmentation for the Erlang distribution protocol. We are using a branch of Erlang that have this high-level Erlang API to be able to support and write your own distribution model in Erlang. We did a prototype of packet fragmentation using this API, and I mean this is really simple. But this is that you get a very a lot more stable round-trip time between two nodes when you send a small message. When the background messages size keep growing, you get more stable round-trip time. So this is things we're going to learn. So that's it. If you want more information, you can go on grisp.org, or you can contact us on IRC or on the Erlang Slack channel. There's a GRISP channel on the Erlang Slack. If you're interested in playing with the GRISP board, playing with Erlang, you can use the discount code to have 20% off during this conference. And that's it. Thank you very much for your attention. And
what's the source license?
What's the source license? Good question. I mean, it's
FreeBSD or FreeBSD or
I think it's FreeBSD because we are really a FreeBSD company. We're using FreeBSD for lots of things. So I didn't set the license on this code, but I would say this FreeBSD.
Use, right?
Sorry?
There are no issues with commercial
No, there's no issue with commercial use. I mean, this is a project. I mean, we actually do that. This is not a commercial product for us. We actually use this design for other products, and we say, okay, we are doing this for other things, for prototyping or stuff. Let's make it and.
Basically, anybody can take it and do whatever they like, right?
Yeah, this is so people have a way of playing with Erlang on the metal.
Is there any GPL in the libraries?
GPL library, I don't think so. These are, yeah.
Maybe it's Apache or MIT, right?
Yeah, I would have to verify. I'm sorry, I don't have it in mind like this. My bad. Yes.
Talking about the hard real-time straight there, were you trying to implement that directly in Erlang instead of having RTOS do it?
No. So the question was, why do we re-implement hard real-time in Erlang? No, the idea is not to re-implement it in real-time. RTEMS is already a real-time OS, but real-time is not just about having a real-time operating system and just work. You have to really be careful about your priorities. For example, right now on the GRISP, all threads run with the same priorities. And in this case, this is not a real-time operating system because even if you want a very strict deadline, and if everybody has the same strict deadline, you don't have real-time. So the idea is to have to add another scheduler that is the single one that have a very high priority and that is guaranteed to be preempted. And to be able to do that, you need a real-time operating system. So RTIMEs give you the tool to do this real-time setup. But what we're adding is making Erlang being able to use these real-time capabilities of the underlying RTIMEs library.
Is modifying scheduler sufficient to obtain at least one real-time priority?
What do you mean?
Like modifying the Erlang scheduler, is that sufficient to obtain at least one real-time priority? Or do you need still something else?
So what we need is adding a new scheduler with some setup for setting priorities. What we need to add a way for pinning processes to this scheduler so they are never moved away. Or
Is that part of Erlang?
I mean, in Erlang, your process could be run on different schedulers. I say.
You can tie it to one, right?
Yeah. So, I mean, this is something that we have to be thought about. I mean, you really want your process to run on this scheduler and nowhere else, and you want to ensure garbage collection after each messages because you don't want this to be part in your. Yeah. So you put garbage collection after the real-time call, and so you guarantee that this your deadline. What you're working on is really the small one. So this is. Sorry. One more question?
Yeah. Have you done any low power work? I noticed you're working on interrupts.
Yeah.
Doing some interrupts from external devices. You can also see internal interrupts. You use with the process low power. You demonstrated the robot.
So I don't hear you very well. I'm sorry.
I was wondering if you had done any low power work on the GRISP.
Low power work?
Yeah.
Yeah. We didn't do much on this particular device for low power because usually we usually don't. And all industrial use cases are usually plugged. So we're thinking about it. I mean, there's a power functionality there. The Wi-Fi has some extra power functionalities, and it can be switch on, switch off, so you use less power. But yeah, I didn't do much about that. This is supposed to be able to run with quite low power, but I would have to investigate more and to give you more details. So that's it. Thank you very much.